All right, so let's take a look at this system of equations. And we're asked to see if this is consistent. Is it consistent? Okay, so in our when our using we are using our row operations here, and so the first thing we want to do is we want to try to put a one in this position, and that's just because that one would correspond to us like anchoring the variable x1 using the first equation. And because this is a zero, this equation doesn't depend on x1. So let's go ahead and swap it with an equation that does depend on x1. So I would go ahead and my first operation would just be to do a row swap. So row swap, row 1 and row 2. And so then we'll have a 1 minus 2, 3. Again, my goal here was just to get a 1 in that position. Um, 1, 2, 3 minus 1 here now. And then the second row is now 0, 3, minus 6, 8. And the third row is 5, minus 7, 9, and 0. Good. Uh, Now we want to eliminate x1 from the other equations. So we want to zero this value out. So in order to do that, we'll take our 5. So it's nice to have a 1 here because then you know that you're just going to multiply this row by that value, right? So this will be, well, minus 5, I should say. Minus 5 row 1 plus row 3 back to row 3. Good. So if I multiply row 1 by 5, I'm just going to write it lightly up here. 5. 5 times negative 2 is minus 10. 5 times 3 is 15. 5 times minus 1 is minus 5. Good. And now we'll write down our numbers here. 1 minus 2, 3 minus 1, 0, 3 minus 6, and 8. And now 5 minus 5. Oops, I forgot to put my minus sign there. Put the minus signs in. Okay, now 5 minus 5 is 0. 10 minus 7 is 3. 9 minus 15 is minus 6. And 0 plus 5 is 5. Good. All right. Now, I could continue, but I'm seeing two rows that are coming that are looking very similar to each other. That's kind of a danger sign. Why? Let's just go ahead and eliminate this 3 like we would anyway by just taking minus for row 2 plus row 3 back to row 3, and let's see what we get. 3 minus 3 is 0. Minus 6 plus 6 is 0. And then minus 8 plus 5 is minus 3. Now, what system of equations does that represent? Well, this bottom here means that 0 equals minus 3, and that, of course, is false. And so, therefore, we must have an inconsistent system. And this kind of a situation is always going to happen with an inconsistent system where you have some augmented matrix, and what will happen is you'll have all zeros here, but then on this side you'll have something that's not 0. So row of zeros and then something not 0. And this will be indicative of an inconsistent system, no solution to your system. Okay, and so that's kind of what you're looking for when you have an inconsistent system. Now, what if this had changed just slightly so that this had been instead of 3 minus 6, 5, what happens if this had been let me rewrite it over here. 1 minus 2, 3 minus 1, 0, 3 minus 6, 8, and 0, 3 minus 6, 8. So if we had had this system, then when we do this row operation, right, we just get a row of all zeros. And is there any problem with that? There really isn't. There's no problem with that. So if I had 0, 3 minus 6, 8, and 0, 0, 0, 0. This is a fine system, no problem, in terms of the solution set. What this means is that um, you can you have a free variable. In fact, this last variable is going to be our free variable. And so what do I mean by that? Uh, Let me rewrite the matrix on the next page here. I'll pause for a second. Okay, so this is just picking up where we left off. We said that this is the case where this all ended up being 0 instead of having a non-zero value there. What happens in this case? Well, remember what this equation says. This says that x1 minus 2x2 plus 3x3 equals minus 1, and then 3x2 minus 6x3 equals 8. So therefore, x3 is actually a free variable. So we could just write x3 as free. And then you could solve for x2, right? x2, I'm just rewriting it from this equation, would be 8 plus 6x3, and then divided by 3, right? And so x3 then, once you decide on what value x3 is, you can compute x2. And then once you've computed x3 and x2, then you can compute x1, because x1 is minus 1 plus 2x2 minus 3x3. Right? So, and then x3 is free, and then x2 is equal to this. Good. So this is, when you have a free variable, that corresponds to having an infinite number of solutions, because x3 is free to be anything. Okay. Now a row of zeros is not necessarily necessary for this to happen. So just as a easy example would just be, what happens if we just had the matrix 1 minus 2 3 minus 1? Well, in that case, this just corresponds to the plane, right? X minus 2 y plus 3z equals minus 1. And so in fact, you could think of y and z as two independent free variables. So this is free and this is free. And then x could be defined in terms of those two. So in this case, you have two free variables. Okay, so a row of zeros is not necessary for you to have free variables. But if you do have a row of zeros, that might mean that one of your variables is free. Okay, good. So we've now gone through the cases where we have a unique solution. What are we looking for in the case of a unique solution? Well, you want to be able to get to like 1, 0, 0, and then a number here, and then 0, 1, 0, then a number there, and then a 0, 0, 1, and then a number there, and so on. Okay. And then inconsistent situation is where you're going to have, do you remember? Zeros, and then something not 0. Not 0. And then an infinite number of variables or solutions. It's getting late in the afternoon. This means if we get free variables. If we have free variables, that corresponds to the infinite system. Infinite solution to the system. Good. All right. I think that, that just about covers us. Let's try one more quick example here just to finish off what we were doing on the slides. So suppose I have 3x1 minus 9x2 equals 4, and minus 2x1 plus 6x2 equals h. I want to find all the values of h so that this system is consistent. So to start things off, let's go ahead and write down our matrix. And when I'm dealing with a matrix like this, I like to have a 1 in that position. It's not mandatory, but sometimes it makes the easier, the computation is easier later. So let's go ahead and take a third times R1. 1 minus 3, and then 4/3. And then minus 2, 6h. Good. And then to eliminate this from your matrix here, we'll go ahead and take 2 times row 1 plus row 2 back to row 2. 1 minus 3, 4/3. And now when I take 2 times this, it'll be 2. Then 2 times minus 3 is minus 6. 2 times this would be 8/3. And then minus 2 and 2 is 0. 6 minus 6 is 0. Uh-oh. Danger sign. 8/3 plus h, so h plus 8/3. And so what is your conclusion? Yes, consistent only if h plus 8/3 equals 0, or h equals minus 8/3. Good. And in that case, by the way, what do we get here? We have zeros, and then just we would have a free variable then. So we would have an infinite number of solutions once our h is if h is negative 8/3. Good. All right. So by the way, if h is not negative 8/3, that means this would be inconsistent, right? Good. I think that gets us through the slides from the class. And so in the next series of videos, we'll take a look at section 1.2.